Chapter 4: The Adaptive Compliant Trailing Edge Investigation. Another important element of NASA's green aviation research involved developing a wing surface capable of changing shape in flight, which would make airplanes quieter and more fuel efficient. This played strongly to NASA's traditional excellence in aerodynamic research, which dated to the earliest days of its predecessor, the National Advisory Committee for Aeronautics. The Adaptive Compliant Trailing Edge, ACTE, is an imaginative morphing wing technology that allows an aircraft to seamlessly extend its flaps, leaving no drag-inducing, noise-enhancing gaps for air to flow through, creating energy robbing, hence fuel robbing, turbulence and vortices. Compliant structures are used to change the wing trailing edge shape to maintain smoothly curved surfaces along the flow direction, thereby avoiding abrupt discontinuities, particularly those aided by conventional hinged control surfaces such as roll-controlling ailerons, lift-enhancing flaps and slats. Compliant structures allowed smooth variation of the trailing edge shape in the spanwise direction, making it possible to seal any gaps at the edges of deflected control surfaces. These characteristics can improve control surface effectiveness and also provided the ability to tailor spanwise aircraft load distribution to enhance aerodynamic efficiency, reduce structural loads, and generate control forces. A compliant structure is a monolithic jointless mechanism that exploits the elasticity of material to produce a desired functionality such as force or motion transmission, motion guidance, shape changing, and/or energy storage and release. As applied to a device such as an aircraft flap, compliant structures are optimized to distribute localized strain to change the shape of the control surfaces needed during flight. Instead of using a series of mechanical actuators, a compliant structure deforms as a whole, thus avoiding high stress concentrations in localized regions. Known as distributed compliance, this design concept offers additional benefits because the entire adaptive structure can reshape itself into complex predetermined positions with minimal force and can be locked in place at any desired configuration. Although such structures are generally described as flexible, they are actually optimized to resist deflection under significant external aerodynamic loading and provide the same stiffness and structural strength as a conventional flap. 2 Compliant trailing edge flaps are configured to have a seamless surface contiguous with the primary wing surface. Elimination of surface discontinuities results in both lower drag and higher control authority than provided by conventional hinged flaps because a compliant flap increases camber under load, generating more lift, and is more effective in roll and gust load alleviation per degree of deflection. Additional benefits of seamless surfaces include making the flaps less susceptible to icing and fouling from debris, and the seamless transition between the fixed and movable portions of the wing reduces noise associated with the turbulent airflow generated by discontinuous surfaces at the flap ends when the high-lift devices are deployed for landing. 3 There was historical precedent for NASA's work on compliant trailing edge flaps. In 1978, as part of the Joint Air Force NASA Advanced Fighter Technology Integration (AFTI) program, the Air Force Flight Dynamics Laboratory, FDL, now enfolded within the Air Force Research Laboratory, launched a Joint Air Force NASA program to build and test a so-called Mission Adaptive Wing, MAW. The MAW, an outgrowth of aerodynamicist Richard T. Whitcomb's brilliant conceptualization of the so-called supercritical wing, SCW, earlier tested on a modified Vought TF-8A Crusader, was a smooth variable camber relatively low aspect ratio wing which, via a series of internal actuators and linkages, could be adjusted for optimum transonic and supersonic flight performance. Following tests of competing industry designs in the Langley 8 featuring transonic pressure tunnel, Boeing received a 1979 contract to fabricate the new wing, which was subsequently installed on a modified General Dynamics F-111A airplane, SN63-9778, already flying with an experimental NASA-developed SCW as part of the Air Force NASA Transonic Aircraft Technology Program. Over 59 flights totaling 145 flight test hours from 1985 through 1988, the AFTE F-111A MAW demonstrated that such a wing could afford significant aerodynamic and performance advantages. Cruise performance showed an approximately 7% reduction in drag, supersonic range at low altitude increased by 25%, and the plane had 30% greater range at high altitude than a conventional F-111A, though weight and complexity of the mechanical actuation system hindered its further development at that time, and some promised modes of camber control remained unexplored. 4 From the mid-1980s through the early 1990s, a succession of wind tunnel test programs had shown that an aeroelastic wing, one thin and flexible enough to have reduced torsional stiffness, in contrast to a conventional wing, which deliberately has a robust structure to minimize loads induced deformation, would also have greatly enhanced control power, the ability to be flexed as an entire surface for enhanced roll control and also for loads alleviation. Additionally, Gross weight could be reduced significantly, perhaps by as much as 20%. As a consequence, in 1996, NASA, in conjunction with the Air Force and Boeing, to whom Lockheed Martin, British Aerospace, and Moog Incorporated were subcontractors, began the Active Aeroelastic Wing (AAW) development and flight validation program, a major step forward towards creating a bird-like morphing wing, one where the aeroelastic response of the wing itself could be exploited to deform the wing's shape into one, furnishing optimum aerodynamic performance and flight loads distribution across the range of an aircraft's flight envelope. 5 As they had earlier with the AFTE F-111A MA, Boeing engineers, in conjunction with their military and NASA counterparts, took key structural and other components from the wings of a retired NASA FA-18A, the former, High Alpha Research Vehicle, HARV, NASA 840.6. They added a drive system for cycling independent outboard and inboard leading edge flaps, and replaced the plane's thick wing panels with thinner panels fabricated from aluminum and titanium with solid composite skins, reducing the wing's torsional stiffness by approximately 17% over the baseline FA-18A. In effect, they were restoring the FA-18 wing to the original very elastic thin structural design that had characterized early production models. The modified wing incorporated new high-rate actuators that, driven by a new flight control system, could deflect the wing's surface, similar to the wing warping the Wright brothers had employed on their 1903 Kitty Hawk Flyer. The new wings were then joined to a Navy-furnished airframe, the resulting new FA-18A becoming the NASA 853. In 2006, the FA-18A was designated the X-53, though it is best remembered by its original name. 7 extensive ground tests, including tests of a scale FA-18A model in the NASA Langley Transonic Dynamics Tunnel in July and August 2004, preceded Phase I flight testing, which included functional check flights, aeroservoelastic clearance flights, aerodynamic and loads model development, and envelope expansion. Phase I commenced in November 2002, and concluded in April 2003 after 50 test missions, during which the FA-18A flew to Mach 1.32, approximately 914 miles per hour, at 24,800 feet. Following extensive preparations including exploiting Phase I acquired data to update aerodynamic and loads databases, and others necessitated by the complex nature of the closed-loop control laws testing to come, Phase II commenced in mid-December 2004 and continued through the end of March 2005. Testing went smoothly, including full deflection 360-degree rolls validating full-scale AW performance, and concluded in less than 4 months, after a total of 34 Phase II flights. Overall, the FA-18A was a great success, proving the practicality and benefits of active aeroelastic control. 8 Though undertaken for very different purposes, the F-111A MA and FA-18A thus constituted important predecessor steps before the onset of the ACTE investigation. It began in the summer of 2014, when researchers at AFRC replaced the conventional aluminum flaps, speed brakes, and spoilers of the Armstrong Flight Research Center's Gulfstream Aerospace G3, NASA 804, with advanced, shape-changing assemblies that form seamless bendable and twistable surfaces. A series of flight tests from November 2014 through April 2015 explored the feasibility of using such flexible trailing-edge wing flaps to improve aerodynamic efficiency and reduce noise generated during takeoffs and landings. Employment of ACTE technology would also result in size and weight reductions for aircraft wings, leading to reductions in fuel burn and greenhouse gas emissions. Other potential aerodynamic benefits of ACTE include increased control effectiveness and alleviation of structural loads. ERA researchers concluded that the results of flight testing successfully increased the ACTE technology TRL to 6.9. According to CODA, the aerospace community has known for a long time that if you have a seamless wing that can be morphed in flight to maximize performance, then you can get significant fuel efficiency. In the earliest days of aviation, various designers, the Wrights, Louis Blériot, Louis Bechereau, Robert and Léon Morin, Igor Itrich, Tony Fokker, Jeffrey de Havilland, and Igor Sikorsky, among many others, used wing warping for controlling their wood-and-fabric aircraft. Later use of metal alloys for structural strength precluded designing aircraft with morphing wings, but the advent of strong, lightweight flexible materials made it possible to revisit the concept. While looking at this problem in the early 1990s, CODA came up with an idea he called compliant design that used techniques borrowed more from nature than from traditional mechanical design. 10 In conventional aircraft construction, everything that is strong is also very rigid. Mechanical functionality requires multiple parts and complex mechanisms. Designs in nature are different, he explained. They are strong, but they are compliant, they're flexible, You can see countless examples in nature of intricate mechanical motion without conventional joints. In Coda's flex foil system, every part of the structure shares a small portion of the total load. Stresses are evenly distributed. You have large deflections and small strains, so you can do this multiple times. Throughout the life of the aircraft, you can do millions of cycles and still not fail. Although the exact technique remains a trade secret, Coda explained that a proprietary algorithm minimizes the force it takes to morph the wing into a prescribed shape. This technique also has inherent mechanical advantages in that it remains very rigid toward external loads, and although the design is incredibly strong, it does not require large, heavy motors to actuate the control surface. 11 Specific details regarding the design configuration and materials that make up the ACTE control surfaces remain proprietary, but the potential benefits are known. A morphing surface has the potential to cut cruise drag by around 3% on retrofitted aircraft and up to 12% on all new designs. The shape-changing mechanism exploits the inherent elasticity of the composite material from which it is made, and by using evenly distributed devices rather than flexural hinges, the ACTE flap requires less power to actuate than conventional flaps. The seamless transition region with the wing eliminates a major source of airframe noise, which is most noticeable during takeoff and landing. Additionally, the ACTE flap provides larger system-level weight benefits for all new designs, as opposed to retrofits, because it could be used to twist a specially designed wing spanwise to reduce loading as well as wing bending moment. 12 In the mid-1990s, Coda unveiled his unique concept to Air Force engineers at the AFRL at Wright-Patterson AFB, Ohio, eventually securing SPR funding through AFRL. According to Pete Flick, ACTE project manager at AFRL, the laboratory's investment from 1998 to 2015 totaled around $20 million. NASA ACTE project manager Thomas Rigney said that his agency contributed about $25 million starting in 2009. The NASA portion primarily supported flight testing and modifications to the G3 testbed that included fitting it with special instrumentation and a new power system. 13. According to Rigney, the reason we needed to do this on a full-scale aircraft was to take the readiness level from TRL-5 to TRL-6 in a relevant flight environment. For that you need a full-scale aircraft. This was important because government and industry team members were convinced that ACTE technology had the potential to be a real game changer for the aeronautics community, particularly with regard to its impact on fuel savings. The amount of potential fuel savings is significant, said Rigney, not just for the economy, but for the environment. 14 researchers selected the AFRC-based Gulfstream G3 subsonic research aircraft, SCRAT, as the ACTE testbed because the airplane's baseline flight characteristics were well understood, and the modification process would be relatively uncomplicated. Additionally, the aircraft was already equipped with data acquisition and telemetry systems for transmitting data to the AFRC control room, where researchers and engineers monitor experiments and safety-related information. Necessary modifications included removal of both the left and right aluminum Fowler flaps, each 19 feet long. Technicians replaced these with flexible ACTE flaps, which were mated to the same attach points on the wing as the original flaps. The main portion of each ACTE assembly was blended seamlessly into the wing structure on both ends via flexible transition sections. These had to be both strong and flexible enough to withstand aerodynamic loads and maintain the integrity of the outer mold line while being exercised through large deformations. 15. ACTE ground tests. Ground testing was an essential element of the ACTE project development approach, which incorporated conventional design practices and a build-up test and model validation approach. Throughout the project, researchers conducted a wide variety of ground-based tests to ensure airworthiness of the structure and to mitigate potential risks to schedule and mission success. These experiments included material characterization testing, structural proof testing, structural qualification testing, fatigue testing, and ground vibration testing, GVT. Project engineers employed a methodical building block approach to ground testing so that any design and fabrication flaws could be detected and corrected early in order to minimize schedule delays and cost increases. According to AFRC Aerostructures engineer Claudia Herrera, this method also provided opportunities for the project team to gain early fundamental insight into the compliant structure technology. Before any hardware was subject to evaluation, engineers first used a computational tool called Fem Analysis to build confidence in the validity of their mathematical models. FlexSys then manufactured 2 prototype test articles representative of the ACTE flap design and fabrication process. Ground testing of these articles provided the data necessary to support an accurate airworthiness assessment of the flight article. This was crucial to the success of the project. Not only did these tests provide confidence in the aeroelastic analyses, They also helped determine best practices for testing the flight article. 16 Ground testing included analyses of aeroelastic response through the transit-tie-in sections used to integrate the OCT flap to the G3 wing in a continuous mold line. Researchers evaluated the results to ensure that the combined SCRAT/OCT system was safe to fly within the desired flight envelope. Per AFRC aeroelastic guidelines, the test bed with its integrated OCT flaps was required to demonstrate a 20% flutter margin to satisfy project requirements for airworthiness. To satisfy this requirement, engineers performed vibration testing and used the resulting data to develop a detailed FEM. In order to minimize impacts to the flight schedule while accurately modeling the flight article, FlexSys built two sets of prototype test articles, designated Prototype 2, P2, and Prototype 3, P3, prior to fabricating the OCT flight test articles. The differences between P2 and P3 were essentially minor design, fabrication, and manufacturing process changes that allowed P3 to minimize strain levels when subjected to large deflections. The P3 design possessed the full chordwise size of the flight test article but represented only a section of the spanwise size. Prototypes containing components designated as A were representative of a portion of the main flap section, while those with components designated B were full-scale chordwise transition sections. 17. The engineering team performed GVTs on test articles P2.2b and P3.2b as a proof of concept for testing the compliant structure. NASA personnel conducted both tests at the FlexSys facility in Ann Arbor. The results provided confidence in test procedures as well as data for understanding the modal characteristics of the transition sections needed for validation of the FEM. Both test articles represented the right-hand inboard transition section with only slight variations. Conducted in September 2012, the P2.2b GVT was the first opportunity to experimentally evaluate the structural dynamic response of the FlexSys compliant flap structure. Goals included measurement of vibration frequencies and mode shapes at several deflections and two different boundary conditions. The engineers wished to consider any apparent change in structural stiffness due to changing the flap deflection. They also needed to evaluate several factors including the use of accelerometers as instrumentation on flexible structures, various types of excitation methods and instrumentation mass loading effects, and a variety of analytical FEM techniques. The results provided a comprehensive set of lessons learned on how best to model the OCT flap and how to test compliant structures, and also helped identify possible design variables for updating the FEM. For the P3.2b GVT in April 2013, the test article was a reproduction of the right inboard transition section of the OCT flight article. It included a 3-inch section simulating the main flap portion of the OCT flight article, a 5.75-inch section to simulate the fixed wing structure, and a truncated section of the OCT flap spar with an attachment simulating how the flap would connect to the SCRAT airframe. 18 Engineers analyzed the OCT structure's modal response by deflecting the Octfem analytically using the ANSYS and Nastran software packages to match the planned physical deflections of the structure. To do this, FlexSys first developed a mathematical relation between the amount of input applied at the flap actuation points and the amount of control surface deflection relative to the airplane's fixed-wing section outer mold line. These same inputs were applied at the actuation locations in the FEM. The engineering team then analyzed the deflected structure for natural mode shapes and frequencies using a nonlinear analysis method. During the P2.2b test, researchers noticed that the resulting deflected FEMs did not match the test results as well as expected, and it was necessary to validate each of the deflected shapes against the measured deflected structure to determine which software performed best for creating the deflected FEM of the OCT structure. As a result, validation of the analytical deflected shapes against the measured deflected shapes became an important objective to be satisfied during the P3.2b GVT. Other test objectives for the P3.2b GVT included quantifying changes in frequencies and mode shapes as a function of flap deflection, evaluating various types of excitation methods, and determining what design variables to use in potential future FEM updates. 19 Results of the P3.2b GVT indicated that ANSYS consistently produced more accurate analytical deflection frequencies and mode shapes that better matched the GVT data. Because they took a conservative approach with the FEM and the flutter analysis, the analytical results were lower than GVT results for critical modes. Although a post-test FEM update was not required, the team performed one in order to more accurately determine material properties for the flexible structure. After being validated, these properties were inserted into the full flap FEM, which was also validated and updated using the full flap GVT results. While conducting these tests, engineers noted that a geometry change caused by applying different flap deflections significantly altered the internal loading of the structure. This created an apparent change in stiffness that was manifested in the test frequencies and mode shapes. It became necessary to apply multiple types of excitation to locations on the simulated wing and main flap sections to verify that the modes of interest identified through earlier analysis were adequately measured. The resulting GVT data were used to ensure correlation with analytical models. Testing also produced some unexpected results. Unexpectedly high damping values had to be empirically estimated due to some unique characteristics of the flexible structure, and researchers discovered an unpredicted mode at 30 degrees deflecting. Engineers concluded that the truncated main flap section of the P3.2b test article probably engendered a lack of stiffness in the spanwise direction for the highly deflected flap. 20 The team performed flutter analyses using Zero, a powerful engineering tool developed by Zona Technologies Incorporated, in Scottsdale, Arizona, that integrates essential disciplines required for advanced aeroelastic design and analysis. In order to facilitate this, researchers at AFRC first developed a baseline SCRAT aerodynamic model based on a half model supplied by Gulfstream Aerospace and updating it to reflect the full aircraft configuration complete with OCT flaps. Using a finished model that contained 3021 flat panel elements, researchers analyzed 2 fuel conditions, full and empty, and 3 flap settings from -2 to 30 degrees. Flutter frequency response was calculated for speeds ranging from 0.6 to 0.8 Mach. 21 According to Tom Rigney, the greatest challenge was integrating the OCT flap with the SCRAT testbed. It was a major modification, he said, and it was absolutely critical to get the new flap to fit exactly right. It had to be very closely coupled with the wing. There was little room for error because if either flap was just 1 degree out of alignment, it could make the airplane difficult to control. When the OCT flaps first arrived at Armstrong, they didn't fit just right and we had to work very closely with the people in the machine shop to adjust the flaps and compensate for gaps, and things like that, said Rigney. We were eventually able to meet the requirements, but it wasn't easy. 22 Testing of the complete SCRAT aircraft with flaps installed took place in the AFRC Loads Laboratory. Having access to a comprehensive set of data and accurate loads equations resulted in more precise flight test data and enhanced safety of flight because researchers were able to expand the flight test envelope without exceeding the aircraft's structural limits. Before flying the airplane in the OCT configuration, however, technicians first had to conduct specialized tests that involved applying loads to the aircraft via hydraulic jacks. Scientifically calibrated strain gauges provided researchers with highly accurate measurements of the applied stresses, enabling them to predict the structural performance of the aircraft in flight. According to Chief Test Engineer Larry Hudson, doing a test of this nature enables us to understand on the ground, by applying certain loads into the airplane, what loads will be experienced in flight under similar conditions. 23 Lifting the airplane off the loads lab floor with the 3 inflatable airbags isolated the airframe from any potential influence the landing gear might exert upon strain gauge data. According to Principal Investigator Bill Locos, the center's loads lab had never previously employed this method. Technicians positioned the airbags beneath the wings and aft fuselage to keep the main gear tires off the floor, thus ensuring that loading across the aircraft's center wing box structure remained constant. This was necessary, Locos explained, because increased loading on the wings typically resulted in decreased loads on the gear, which affected the strain gauge measurements and skewed the results of the preliminary equations. Supporting the G3 with standard aircraft jacks was not an option, he noted, because the effects were even more pronounced than those produced by the gear alone. Alternatively, using a cradle system would have been costly and time-consuming. Airbags of the type used to lift aircraft in the field following gear-up landings were already available as proven off-the-shelf hardware. 24 Once the G3 was properly positioned, lab technicians applied loads with hydraulic jacks positioned underneath the wings. Structures lead Eric Miller explained that combining known loads values with strain gauge responses in the lab helped researchers develop a database for validating or correcting existing load equations. We correlate these data so that we can drive our own load equations and be able to monitor flight loads in real time during OCT flight tests, he said. 25 Flight testing OCT now, the team was ready to begin collecting flight test data to validate pre-flight modeling. Based on these analyses, both OCT flap assemblies had been fully instrumented to capture the in-flight aeroelastic response for comparison to a set of predictions for each deflection test point. Engineers in the AFRC Mission Control Room monitored the instrumentation suite via telemetry throughout every flight. Flight test points that could be compared directly to analytical predictions were considered anchor points, but the OCT flaps were also deflected to positions that were not analyzed. The results of these spot checks could be used only to verify trends between anchor points. 26 Prior to takeoff, an aircraft crew member manually excited the transition sections with a few sharp taps, and the response was measured through the onboard data collection system. While flying, engineers used response data provided during various maneuvers to estimate vibration frequency and damping. While airborne, excitation was provided primarily by light turbulence encountered during flight over the Edwards Air Force Base test ranges. After each test mission, the engineers evaluated mode symmetry by comparing recordings of accelerometer signal data. 27 For the sake of simplicity and safety, the actuation system was not exercised during flight. Instead, the ACTE research team developed a build-up approach to flight testing that entailed clearing the ACTE flight envelope through a series of specific test points in such a manner as to strategically increase dynamic pressure and Mach number throughout the performance envelope. Initial flights took place at low altitudes and speeds, followed by tests at high altitude and low speeds. The next step included high altitude and high speed tests and concluded with low altitude and high speed tests. It was a build-up approach, Rigney explained. Each time, we increased the flap angle and airspeed parameters, and we expanded the performance envelope on every flight. 28 During each flight, the AFRC Mission Control Center was staffed to monitor mission critical, safety of test, and safety of flight parameters. The SCRAT crew included 2 pilots and 1 engineer, and each mission was required to be accompanied by a safety chase aircraft. Each test mission consisted of a set of specific flight test maneuvers to validate stability and control predictions, aerodynamics models, structural analyses, and aeroelastic predictions. The high-speed/high altitude envelope provided flight limits for small flap deflections, and the low-speed/low altitude envelope provided flight limits for large flap deflections. 29 During the inaugural ACTE flight, the experimental control surfaces were locked at a 0-degree setting. Although the flaps were not actuated during flight, a set of incremental fixed flap settings were later employed on subsequent test missions to collect a variety of data demonstrating the capability of the flexible surfaces to withstand a real flight environment. Data from each of these test points were combined to extrapolate the behavior of the flap while extending and retracting throughout the flight envelope. We have progressed from an innovative idea and matured the concept through multiple designs and wind tunnel tests, to a final demonstration that should prove to the aerospace industry that this technology is ready to dramatically improve aircraft efficiency, said AFRL Program Manager Pete Flick following the initial test. 30 The first flight went as planned. We validated many key elements of the experimental trailing edges, said Tom Rigney, noting that now the team faced a variety of challenges including a tight schedule. We had to minimize the downtime between flights, and the airplane had not been flown for a long time prior to the ACTE project, which created a lot of maintenance problems up front, he recalled. The NASA maintenance crew thoroughly inspected the aircraft and made necessary repairs. Problems had to be addressed rapidly, and there were some surprises during the first few flights. Once those were overcome, Rigney noted, we had to deal with new schedule pressures because we had less time to complete all of our flights. He said that between flights, the team focused on the time it took to reduce the data, and made every effort to optimize the amount of work done between flights. Normally, you have milestones that you monitor to make sure everything is on track, he explained, but I created what I called inch stones, where everything is monitored very tightly to make sure we were on schedule and doing all the flights that we needed to. He also kept AFRC managers apprised of potential conflicts, so they could resolve them as early as possible. Overall, we hit our mark in terms how many flights we wanted and the amount of time we wanted them done in, he said. It's hard to convey the amount of effort it took when there were so many people working hard at what they do, because when you're successful, you make it look easy. 31 Every aspect of the flight test process was designed to prove the radical new technology with a minimum of risk. Each incremental test point expanded the flight envelope enough to move on to the next step. The decision, made early in the project, to use fixed flap positions instead of actuating the flaps in flight was based on risk reduction and also allowed the team to move forward at an accelerated pace. Actuators for ACTE will be developed using existing technology, said Rigney. We didn't need to test that. Backup instrumentation systems made it possible to continue flying even if one or more sensors failed during a flight. The ERA project was really good at making sure we had enough emphasis on risk management, he said. It was a key factor in our success. 32 The ACTE project achieved a major milestone at AFRC on February 18, 2015, when the modified G3 completed a flight with 15 degrees flap deflection, thus successfully meeting all of the project's primary requirements. Throughout the flight test series, data were taken at points ranging from -2 degrees, up, to 30 degrees, down. Although the flexible ACTE flaps are designed to morph throughout the entire range of motion, each test was conducted at a single fixed setting in order to collect incremental data with a minimum of risk. Following the milestone flight, NASA Armed Integrated Aviation Systems Program Director Ed Wagoner declared, "Reaching our minimum success criteria for the ACTE integrated technology demonstration is a testament to the exceptional cooperation and collaboration toward the success of this flight campaign between NASA, AFRL and FlexSys. Every milestone we achieve helps us to better understand how these enabling technologies reduce aviation's impact on the environment." 33. By the end of April 2015, the team had successfully completed 23 ACTE test flights aimed at proving the airworthiness of the flexible structure and its ability to withstand high dynamic pressures at speeds up to 0.8 Mach and aerodynamic loads up to 11,500 pounds per flap segment at high deflection angles. Despite the complexity of the task, all primary and secondary objectives for the test series were successfully completed on schedule and within budget. "It was a very successful demonstration in that we accomplished all of our primary and secondary goals," said Rigney. "We didn't miss any requirements at all." 34. Moreover, he explained, ACTE technology is expected to have far-reaching effects on future aviation. Advanced lightweight materials will reduce wing structural weight and give engineers the ability to aerodynamically tailor the wings to promote improved fuel economy and more efficient operations, while reducing environmental impacts. It also has the potential to save hundreds of millions of dollars annually in fuel costs, he said. 35 Researchers incorporated the results of the ACTE flight tests in subsequent LA-RC design trade studies for future large transport aircraft. Armstrong's work with ACTE is a great example of how NASA works with our government and industry partners to develop innovative technologies that make big leaps in efficiency and environmental performance, said Ha-Won Shin. This is consistent with the agency's goal to support the nation's leadership in the aviation sector. 36. Evaluating future ACTE applications. Every now and then, NASA research leads to innovations that become industry standards. Two excellent examples include winglets and supercritical wings. Both represent simple, yet elegant, solutions to the problem of making airplanes more aerodynamically efficient. When first introduced in the early 1970s, these technologies seemed revolutionary, yet today they are commonplace, having been integrated into a wide range of civil and military aircraft. Based upon its success in testing and its relatively high TRL, it is likely that ACTE technology will be similarly received by the aviation industry. Several analyses of ACTE and similar technologies reported aerodynamic advantages derived from adaptive trailing edges. Sridhar Kota and others at FlexSys and AFRL projected a 3.3% improvement in cruise lift-to-drag ratio for a conventional medium-range transonic transport retrofitted with ACTE flaps. 37 NASA researchers at LA-RC conducted a study using the Center's Airborne Subscale Transport Aircraft Research AirStar testbed, a 5.5% dynamically scaled, remotely piloted, twin-turbine, swept-wing, generic transport model designed to provide an experimental flight test capability for research experiments pertaining to dynamics modeling and control beyond the normal flight envelope. In this case, the AirStar was used to demonstrate flap camber shapes optimized with a vortex lattice coated multiple cruise conditions. The results showed induced drag improvements ranging from 1.2% to 9.9% depending on flight condition and the rate at which camber was allowed to change in the spanwise direction. 38 A study at the University of Michigan examined the application of morphing trailing edges to a conventional long-range, twin-hull transport configuration. Using a Navier-Stokes-based aerodynamic optimization of a variable camber trailing edge flap on a 777 size aircraft, researchers projected drag reductions from 1% at on design conditions to 5% at off design conditions. 39 In May 2013, NASA sponsored a Boeing study evaluating the comprehensive effects of ACTE technology on a variety of commercial transport aircraft applications. Study goals included quantifying changes in weight, drag, and fuel burn caused by the introduction of ACTE technology to 3 aircraft configurations: a 224-seat HWB, a 222-seat conventional wide-body transport, and a 154-seat conventional narrow-body transport. Both the HWB and wide-body transport were designed for 8,000 nautical mile range at 0.85 Mach cruise speeds. The narrow-body transport was designed for 3,500 nautical mile range at an average cruising speed of 0.785 Mach. For the purpose of the study, conventional 11 and aileron controls on the outboard wing of the HWB were replaced with ACTE surfaces. Researchers converted the aft portions of the flaps on the tube and wing wide-body and narrow-body configurations to ACTE surfaces, allowing the flaps to be extended as single-slotted Fowler flaps in low-speed conditions to preserve high lift characteristics. 40 With flaps retracted for high-speed flight conditions, ACTE allowed the flap trailing edges to both control roll and alleviate aerodynamic loads. The latter thus made possible tailoring span loading over a wide range of flight conditions and thus achieving more structurally efficient span loadings in critical structural design conditions, as well as achieving more aerodynamically efficient span loads in cruise. Having the capability to reduce bending moments through load alleviation made it possible to incorporate wings with lower structural weight than is typical, and improvements in cruise span loads resulted in lower drag. Both of these characteristics contributed to reductions in fuel consumption. The study also revealed some penalties derived from using ACTE technology. These included higher weights for control surface structures, control surface actuators, and hydraulic systems needed to power the larger actuators. These weight estimates were based partially on results from the ACTE G3 flight demonstration AFRL and might be offset by future improvements to the technology. 41 Each configuration in the Boeing study was evaluated with and without application of ACTE technology. Because each model had a fixed wing area and engine thrust, the results demonstrated only the direct effects of ACTE, but not the augmentation of effects that would result from changing these variables. The benefits derived from the use of ACTE varied among the different aircraft, and were largely driven by the effectiveness of control surface arrangements, and the importance of wing weight reduction for each aircraft configuration. Researchers plan to use these results in subsequent studies to model the integrated effects of ACTE in combination with other technologies, as well as in scaling effects. 42 Results of the initial study showed that the 224-seat HWB configuration derived the least amount of benefit from ACTE. Researchers found that the benefits of ACTE on span loading and load alleviation could have been accomplished just as easily with less weight penalty using the original control surfaces. Although some additional aerodynamic benefits might have been achieved by closing control surface gaps, these effects were beyond the analysis methods used in this study. The most significant benefit demonstrated was a mere 0.7% fuel burn reduction. 43 ACTE surfaces were added to the aft portion of the flaps on the 154-seat narrow-body transport model. These flaps were configured with typical single-slotted Fowler motion to provide high lift capability, but the ACTE surfaces could be actuated even with the flaps stowed for high-speed flight conditions. In this case, the ACTE surfaces were used primarily for load alleviation and roll control. Researchers discovered that when taking some responsibility for roll control away from the ailerons, the ACTE surfaces freed the ailerons to be partially used for load alleviation. Additionally, use of the ACTE surfaces to transfer loads for roll control inboard effectively reduced bending moments during critical rolling maneuvers. In this configuration, ACTE technology provided a net benefit of 0.9% reduction in fuel burn, which was somewhat better than in the HWB configuration. 44 The greatest benefits resulted from the 222-seat widebody transport with ACTE surfaces added to the aft portion of the flaps. These modified surfaces worked with the outboard ailerons to provide load alleviation while the inboard ailerons were responsible for roll control. Although the original control surfaces could have provided effective load alleviation by themselves, the application of ACTE technology demonstrated larger benefits because the control surface arrangement was favorable for load alleviation, and because wing weight reduction had greater vehicle level effects. Altogether, this configuration resulted in a 2.6% reduction in empty weight, 2.4% reduction in takeoff weight, and a 3.0% reduction in fuel burn. 45 The Boeing researchers concluded that the arrangement of control surfaces may have a strong influence on the benefits of ACTE, and that optimization of the sizing and placement of control surfaces would better define the limits of this technology. They also noted that trading load alleviation benefits against penalties for control surface structure and actuator weight could also allow aircraft designers to size control surfaces in such a way as to provide greater load alleviation benefits. Most important, they felt that with further work ACTE technology could contribute significantly to fuel burn reduction. 46 NASA researchers simulated the radiated sound field produced by a full-scale Gulfstream G3 aircraft during landing. NASA